Welcome to section 2.2, polynomial functions of higher degree. Yesterday we solved quadratics and some other polynomial functions, but mostly quadratics, and now we're going to take that idea and expand it into polynomials, degree 3, 4, possibly 5. Couple of things. We're going to find zeros of a polynomial function. We're going to write the polynomial function given the zeros as well. So we're going to work forwards, and then we're also going to work backwards. A couple definitions we need to take care of first. A polynomial function of x with degree n can be written. It looks complex, but the higher you get in math, you get more notation you kind of get into. Don't be scared of what you see here. You can just see that these a sub n and a sub n minus 1 and so on, those are just your coefficients of the x variable. And then the same thing happens on the next part with the x sub n. You have your x sub n. So let's say that's x raised to the 5th, then you have x raised to the 4th, x raised to the 3rd, x raised to the 2nd, x, and then x to the 0, which would be a constant, or which would be a value of 1. So that's what a polynomial function looks like in generic terms. The degree of a polynomial function determines. Now, what does the word degree mean? Remember, degree is the highest exponent of the polynomial function. So that will tell you a couple different things. It'll tell you the general shape of the graph. It'll give you the maximum number of relative max and mins. Now, relative max and mins we'll talk about in just a little bit. It's not going to be our main focus, but we'll talk about it. It'll give us the maximum number of x-intercepts, which is really going to be our focus. X-intercepts represent the zeros, like we were solving with quadratics. And then also the maximum number of roots as well. And roots can be real, or we could actually get into the complex number system. Graphs of polynomial functions are continuous with smooth rounded curves. We don't have any breaks in the graph. Our domain will always be all real numbers. We can plug in any value that we want. So they're always going to be nice, continuous, smooth rounded curves. Now I'm just going to give you a quick idea of the general shape of polynomial functions from degree 1 to degree 5. Degree 1, these first couple we should be familiar with. Degree 1 is linear, so it'll be a line. Degree 2, you guys know, is a quadratic. Could open up, could open down. Either one is fine. A cubic, if I just graph x cubed the way it is on there, it would look like this. But it could also potentially, depending on what things you add and put onto the cubic, could look more like that. X to the 4th, you might have a couple more curves in the problem. And then x to the 5th, once again, you could have a couple more smooth curves as you get higher in the degree. It doesn't mean you do, it just means that you can, possibly. So the next one, we're going to talk about the zeros of a function. The zeros of the function are all real numbers x, such that f of x equals 0. Now remember, f of x is the same thing as y. So what we're trying to find is, as I told you guys in quadratics, is that you're looking for that x value when y is 0. Alright, and if you think about that, if you're looking for the x value when y is 0, then you're looking for these values on the x-intercept. Okay. So the zeros of a polynomial function, some of the things that you can identify in terms of the zeros of the polynomial function for all polynomial functions of degree n. So we're talking about, once again, the degree of the polynomial. Two things. The function has at most n zeros, at most. Okay, so it can't have any more than that. If it was a degree of 8, you could have at most 8 zeros. Zeros, once again, we kind of interchange some of these words. There are some slight differences, but you got zeros, roots, solutions, x-intercepts, all have very similar meaning to them. And then also, the graph has at most n minus 1 relative max and mins, or relative extreme. So if I graph something, just to kind of give you an idea of what these relative max and mins are. The relative max and mins, because we don't really have a max and a min in this problem, but we have these relative max, min, max, min. So as it goes down, as the shape changes from increasing to decreasing or decreasing to increasing, there's a change in the graph, and that would represent, a relative max for this one, just a relative, and then a relative min, and then so on and so forth. So you could have at most n minus 1. So you can only have, you know, one less than the degree of what polynomial function you're looking at. So once again, just some general ideas as to what polynomial functions are, and some of the things and terminology that we will be using as we go along. Purpose today really is to be able to find all real zeros of each function. So what we're going to be doing is solving, and our focus today though is going to be on solving by factoring. So we'll get into some other methods as we get going, but focus today is going to be solving by factoring. So let's go ahead and get into this. We did some of these things with quadratics, even though we did more than quadratics, so some of this stuff should look familiar as we go along here. So we're going to start with x to the 4th minus 8x squared minus 9. We did one like this the other day where we had to factor. All right, we want to set the y value equal to 0, and we want to factor this. This is quadratic in form. It's trinomial. Instead of x squared and x, we have x to the 4th and x squared. So we're going to factor this, and it'll be x squared times x squared. And then you're looking at, you know, what are factors of negative 9 that add to give you negative 8? So we know that is negative 9 plus 1. So if you double check that, it gives you a factor of negative 9, but it adds to get your middle term of negative 8x squared. And then now you can actually factor the difference of squares, x squared minus 9 to x minus 3 and x plus 3. You can't factor the second one because you can't factor a sum of squares. You can try it, but there's no way to get your middle term to cancel and still get a plus at the end. So because the directions say find all real zeros, we really wouldn't be solving for the x squared plus 1 because it would give us an imaginary solution. So we would set all factors equal to 0, x minus 3 equals 0, x plus 3 equals 0. I'm going to go ahead and set the x squared plus 1 equal to 0 just to show you. But we would get x equals 3, x equals negative 3. And then on this one, if I did solve, I would get the square root of negative 1, which would be x is equal to plus or minus I. But because it only asks for the real zeros, I'm only going to list the real ones. So x is equal to negative 3 and 3. And so in terms of the degree, we have at most n solutions, and we do have 4 complex solutions, including the plus or minus I and the negative 3 and the 3. I'll be right back. Alright, and so moving on to the next one here, we got g of x equals 3x cubed plus 2x squared minus 27x minus 18. This is a method called grouping that you had learned in Algebra 2. So you're going to group the first two, and then you're going to group the last two. So I'll show you that method if you forget. You take out the GCF of the first two, which leaves you with x squared, and then 3x plus 2. And then you take out the GCF in the next one, which would be minus 9, and that will leave you with 3x plus 2. And then what you have here is you have a binomial as a GCF, so we're going to factor that out. That'll leave us with x squared minus 9, and once again that x squared minus 9 is a difference of squares, so you can factor that as well. And we're looking at the potential of having 3 possible zeros on this one, and these look like they're all going to be real. So you got 3x plus 2 equals 0, x minus 3 equals 0, x plus 3 equals 0. Subtract 2, divide by 3, negative 2/3, x equals 3, and x equals negative 3. Alright, so we have 3 real zeros, so we'll write all those down. X is equal to, I usually write mine in order, so negative 3, negative 2/3, and 3 as my solutions. Alright, let's go to the very last one. This one has a degree of 5, so we have 5 potential solutions or roots on this one. So let's start this one. Once again, we're factoring all these. First thing you check for factoring is always GCF. So we have 0 is equal to, and you can take out a negative 2x cubed. That'll leave you with an x squared minus 1. And then from there, you can actually factor the x squared minus 1 because once again, it's a difference of squares. And now you have what looks to be 3 factors, but I'm going to show you something here. This is negative 2 times x times x times x times x minus 1 times x plus 1. So when you see this degree of 5, you actually see 5 potential factors there. It's just that if you set them all equal to 0, you would have x equals 0, x equals 0, and x equals 0. So right here, these are repeating. This is something we're going to talk about later on as we move forward. But for right now, there are 3 of them, but they all equal the same. And then we'll also have the x minus 1 is equal to 0, so that's x equals 1. And then the x plus 1 equals 0, so that would be x equals negative 1. So when you look at this, what looks to be negative 1, 0, and 1, but we also know that x equals 0, when we look at it, has 3 factors. So if you include those, you have how many potential roots? 1, 2, 3, 4, 5, which gets back up to that degree, even though x equals 0 repeats 3 times. So these are things that we'll continue to talk about as we move forward in chapter 2, but as of right now, and once again as today, we're really just focusing on being able to find the roots of polynomial functions by factoring. So, alright, let's go ahead and move forward. We have one more thing to talk about. We're going to work backwards on these polynomials. So, find the polynomial functions with the following zeros. So, if you look at a problem in terms of when you get to the end, we're going to take these ideas and we're going to start with x equals 3 and then work backwards by subtracting 3 to both sides. I'm talking about this one right here. And then working backwards to this, and then working backwards to this, to here, until we all the way get back to the original problem. So I'm going to do that on this first one. We're going to say x is equal to negative 1/2. X is equal to 3. X is equal to 3. And x is equal to 0, and then we're just going to work our way backwards. So on these last 3, you would subtract 3, you would subtract 3, and the last one, it's already equal, so x is already by itself and it's equal to 0, so you're fine there. On the first one though, we don't want a fraction, so we don't want to just add 1/2 to the other side. We want to multiply it by 2, so it'd be 2x equals negative 1, and then add 1 to the other side. So now what you're looking at is 1, 2, 3, 4 factors that we have to multiply together. So we have 2x plus 1, x minus 3, x minus 3, and then x. And how you multiply those 4 things together is completely up to you. So I'm going to multiply the x minus 3. So that 2x plus 1, x minus 3 squared would be x squared minus 6x plus 9 times x. I'm going to multiply the binomial and the trinomial, so that'll give me 2x cubed minus 12x squared plus 18x plus 1x squared minus 6x plus 9. I'm going to simplify that, and then I'll multiply everything through by x. So let's see what we get. We got 2x cubed. I'm going to combine the negative 12x squared and the positive x squared, so that'll leave me with negative 11x squared. And then we're going to combine the 18x and the negative 6x, so that's plus 12x, and then the plus 9, and all of that gets multiplied by x. So we want to write it as a polynomial function. So we'll say f of x equals 2x to the fourth minus 11x cubed plus 12x squared plus 9x. And so once again, if you look at this problem and you start from the end and work your way the other way, that's how you solve. So the same way we're going to do is we're just going to work our way backwards, create the solutions or the factors, and then multiply those factors together to get the polynomial function. Okay, so the last one we're going to look at here is negative 5 times 2 plus or minus the square root of 11. So we're going to do something a little different here. We'll say x is equal to negative 5. Add 5 to the other side to get x plus 5 is equal to 0. And then we got the 2 plus or minus the square root of 11. And if you look back from completing the square, and I might show this in a separate video as well, but if you look from completing the square, in terms of how you solve a quadratic by completing the square, this is what we're going to work backwards from. And so we get the plus or minus the square root of 11 by itself, and then we will square both sides. So that will leave you with x squared minus 4x plus 4 is equal to, and the square root goes away and the plus or minus goes away, and that will leave you with x squared minus 4x. Subtract the 11, so that will give you negative 7 is equal to 0. And now you have your factors, x plus 5 and x squared minus 4x minus 7. And then those are the factors that you have to multiply together. So multiply those two together and you'll get x cubed minus 4x squared minus 7x plus 5x squared minus 20x and then minus 35. Combine your like terms and you have the function f of x equals x cubed minus 4x squared plus 5x squared would be plus x squared. It looks like we got minus 7 and minus 20, so that's minus 27x and then minus 35 at the end. So once again, this is something that I'm going to actually show you a little bit more of in class in terms of why this works and how it works. And I'll do that in the class as well. But for right now, so once again, just going back and seeing what we did here is we talked about the basics of what a polynomial function is, talked about some of the similarities in the graphs, we talked about the zeros of the functions, what they are, where the graph crosses the x-axis. We solved these problems using factoring, different ways, quadratic and form, grouping, GCF, and then we worked backward with some rational solutions, and then we also dealt with an irrational solution as well. So we'll continue this stuff as we move forward here in terms of solving other ways besides factoring.